In Chapter 8, we're going to look at how to write chemical reactions and equations. Ultimately, our goal here is to be able to predict the results of a chemical reaction. So we're going to be using chemical symbols, formulas, a little bit about relative amounts, kind of some mole ratios, to ultimately figure out if chemicals react, for example, A and B, what are they going to make? In section 1, we're going to go through a couple of the pieces. Really don't get into the big stuff until section 2. So in section 1, 3 things we're going to look at. Number 1, how do we know whether or not a chemical reaction has really occurred? What are some signs? What are some indications of that? Number 2, again, continue to be familiar with writing formulas of chemicals from their words or from their names and vice versa, kind of working back and forth. And then the last thing, be able to balance equations. If we're able to balance equations in terms of number of atoms, then that does give us a sort of a ratio or proportion of relative amounts if we can count atoms. So first of all, how do we know a chemical reaction has really occurred? Just because we mix two things together, we don't. How do we know that there was anything that changed? How do we know we just don't have the same things that we started with? So 3 fairly obvious things that we know a chemical reaction has occurred. And at some point, obviously, we'll show these in class. So number 1, a chemical reaction occurs, and there's heat and there's light. So we got fire and flames. If definitely we have a fire or flames, it's an exothermic reaction. There was probably a certain number of chemical bonds being broken and or formed. Now, heat without light, not necessarily. Just because something gets warm, that does not necessarily mean a chemical change. Number 2, production of a gas. Okay, most common way is usually when you pour a liquid into a solid. You've all seen a fairly simple example used in junior high or maybe in elementary school. Plain old baking soda and vinegar. Perfect example. And then the last one, formation of a precipitate, a fancy word for solid. We've been doing a lot of these reactions already this year. We mix 2 liquids together and we get a solid. 2 clear liquids and we get a green solid. A white liquid or a clear liquid and a yellow liquid and we get a white solid or whatever possible combinations there could be. Now, can there be other ways to know that a chemical reaction has occurred? Sure, but these are 3 obvious ones that we know without a doubt. Now, when we're starting to write these chemical equations and these chemical reactions, there are 3 things that we need to make sure we have in these chemical equations. Otherwise, it's going to really mess us up down the road. Number 1, obviously it's got to represent the facts. Somehow, some way, this equation has to tell us exactly what happened and what was involved. Number 2, we've got to have correct formulas and symbols. If we can't write the correct formulas and can't have the correct symbols, then we're done for. So if we really go into this, this is all the stuff from 7.1. So you still got to know sulfate, nitrate, chlorate, carbons, a +4, -4 oxidation state. Iron is a +2, +3, +6. All those things still hold true. Number 3 then, you got to be able to show the relative amounts. So once we start to balance these equations and have the atoms counted, we do know something about amounts that are involved in the chemical reactions, more specifically mole amounts. And we'll get to that here in a little bit. So these 3 things have to be in every reaction, every equation. All right, next thing here, and really this is kind of the last thing before we actually jump into the section. There are these 7 elements, or what we refer to as diatomic molecules. What we mean by this is when we talk about elements free in nature or elements by themselves, they are just single atoms. Well, these 7 elements are fairly reactive. So when we talk about finding these elements in nature, we're really not finding them alone. We are finding them in pairs because they're a little bit more reactive. So whenever we say hydrogen gas, it's not H, it's H2. When we talk about when we breathe in oxygen gas, we're not breathing in oxygen atoms, we're breathing in oxygen molecules, 2 oxygen atoms that are bonded together. This is important because as we start to write formulas and balance equations, we need to recognize that these 7 are diatomic. every other element that exists. We say sodium reacts with, carbon reacts with, um, potassium reacts with, phosphorus. We're talking about single atom ions. But again, these seven, they are diatomic. They're always in pairs. So you got the four halogens and then hydrogen, nitrogen, oxygen. Just got to know them. All right, so first thing, we're going to take word equations, okay, and we're going to change them into formula equations. So what we'll have here is a chemical reaction that's in its word form, and we have to be able to change those words into formulas. So look at the first example here. Sodium chloride plus silver nitrate forms silver chloride plus sodium nitrate. So all we're going to do is change these words, these chemical names, into their corresponding formulas. So sodium chloride. Sodium's a +1, chloride is -1. We get NaCl. Silver is a +1 charge. Nitrate is a -1 charge. AgNO3, +1, -1. Forms, okay, that's what the arrow talks about. It's producing, it makes silver chloride. Ag is +1, chloride is -1. AgCl. Plus sodium +1, nitrate -1. NaNO3. So what we have here is a chemical equation, a chemical reaction. NaCl plus AgNO3 forms AgCl plus NaNO3. One of the things that we will notice here as we get into section 2, we got sodium with chlorine, and now we've got silver with chlorine. We have silver with nitrate, now we have sodium with nitrate. A phrase that I'm going to use a lot in this chapter. Metals trade places. Most important phrase that I will say in this chapter, and the phrase I will say not only most important, I will say it the most often. All right, let's look at another one here. Iron 3 sulfate plus copper 2 chlorate makes iron 3 chlorate and copper 2 sulfate. So what I want you to do here is just pause this for a second. Again, you should start to feel more comfortable writing formulas and balancing checking charges and all that stuff from chapter 7. So I want you to pause this for a second, figure out what the formulas are, what the charges are, and then come back and see if you agree with what I have. Okay, so you see here, I have the formulas written out, and then I have the equation here written at the end. Iron 3 plus sulfates SO4 2 minus, and again, needing to know what all the formulas are and their corresponding charges. Now, one thing you might begin to notice here, and we'll talk about in a little bit, I got 2 irons here, but I got 1 there. How can I have a different number of irons? Where did they go? Well, that's balancing. Like I said, we'll be there in a little bit. So if this was you're still struggling with this, you got to go back into chapter 7, section 1, and keep looking over names and formulas and all that stuff. All right, now we're not going to do this very often because we want formulas so we can have molar masses so we can do calculations. But for practice and for homework, occasionally they're going to have you take the formulas and put them back into words. So real quick, NaCl, sodium chloride, plus AgNO3, silver nitrate, forms NaNO3, sodium nitrate, plus AgCl, silver chloride. Okay. So again, we're not very infrequently are we going to go from formulas back to words. It just gives us more practice kind of figuring all that stuff out. The majority of the time is going to be getting formulas and writing formulas. All right, next thing, other things we include in chemical reactions. There might be additional symbols or special conditions or something we want to emphasize within a reaction. The most common thing that we're going to talk about are what are called phases. So when we write a chemical, we don't know if the chemical is a solid, a liquid, a gas, or whatever it is. So one of the first things we're going to talk about are these four symbols: liquid, gas, solid, or aqueous. Now, if you see the word AQ, again, it stands for aqueous, which means the chemical has been dissolved in water. So just two simple examples here: NaClS and NaClAQ. NaClS is talking about solid sodium chloride. You've got table salt in your hands. NaClAQ is salt water, salt that has been dissolved in water. H2OS, H2OL. H2OS is ice. H2O liquid is plain old water. Again, this will be important later. You are not going to know what they are just by reading a question or anything like that. All I want you to do is, if you see them, copy them down. So you can't predict yet. Just copy if you see. Okay? So just copy them if you see them. And that's all we're going to do with this so far. There will be later chapters where we can predict whether or not it'll be a solid, liquid, or gas. All right, next thing, you may see something written with the arrows, above or below the arrows. Well, those are often referred to as special conditions. Maybe we got to have a unique temperature. Maybe there's got to be an extra chemical involved, something we call a catalyst or something else. It could be something, something as simple as, well, the reaction's not going to work unless it's at least 200 degrees Celsius. Or the reaction's not going to work if it's at least a certain pressure. The gases are under a certain pressure. Now, something a little bit more bizarre is the reactions aren't going to work on Tuesdays. Well, obviously, it's not necessarily the case, but that is a special condition. We also will see sometimes reactions, we're not going to talk about them now, but are two-way reactions. They can go one way, and then the chemicals that are produced turn back. This is not something we're going to spend a lot of time on, but you may see these once in a while. Okay? All right, then the last thing, and this gets into a little bit of the math portion. Now what we're going to talk about is balancing the chemical equations. So what we're talking about balancing equations is the number of atoms that we have before the reaction begins has to equal the number of atoms after the reaction is over. We can't just magically gain carbon atoms or just somehow weird and we lose oxygen atoms. What's in the reactants must still be there somehow in the products. Because what a chemical reaction really is, it's a rearranging of atoms. We're not creating them, we're not destroying them. So all atoms do are rearrange. So it's very simple, the counting. Number one, first of all, when you write chemical formulas, you've got to get the right formulas, you've got to have the right charges, you've got to have the right subscripts, and then don't change them. We never change subscripts. Okay? Those subscripts are based upon the correct formulas and the correct charges, and then we don't touch them. After we've done that, we use coefficients in front of the formulas to balance the number of atoms on both sides. Okay? And then the last thing, and this kind of helps out, whenever we're counting, just leave oxygens and hydrogens last. The reason being is, if obviously it's got oxygen or water or hydrogen gas somehow in the equation or the reaction, and usually it kind of just takes care of itself. Okay? So let's do a simple one here. Hydrogen gas plus oxygen gas makes water vapor. So don't forget back at the beginning of this section what we talked about when we talk about hydrogen gas. Hydrogen is a diatomic element. So it's H2. H2 reacts with oxygen gas, O2. Okay? It's also diatomic and forms water vapor, steam. Okay? So we've done the first step here. Determine the correct formulas and don't change them. Okay? H2 plus O2 makes H2O. Now, right off the bat, you say, wait a second, I got two oxygens on the left. Where'd the other one go? We're not done yet. So, once we have the correct formulas, now we use coefficients in front of the formulas to balance. And both sides have got to be the same. So I come out in front here. And I like to say, okay, on the left-hand side, I've got 2 oxygens. On the right-hand side, I only have 1. So I need to put a coefficient out in front to get the correct number of oxygens. But if I put a 2 out in front, now I've got 2 oxygens on each side. But now you recognize that I have 2 hydrogens on the left, and now I have 4 on the right. So I put a 2 out in front of the H2. Now, what are we really saying here? Well, what we're saying is I have 2 pairs of H's, and they react with 1 pair of oxygens. When they react, the 2 H's bond with one of the O's, and the other 2 H's bond with the other remaining O. And there's we get 2 water molecules. So all we're really saying is 1 hydrogen and 1 oxygen does not make 1 water. It takes 2 hydrogens and 1 oxygen to make 2 waters. And that's what we say when we're balancing equations. Okay? That's what I do is just keep practicing. So here's what I want you to do is we'll do the first one here together, and then have you work on the next 2 kind of on your own. So just pick an element. All right, sodium. I got 1 sodium on the left. I got 1 on the right. Done. I'm going to pick calciums next. I have 1 calcium on the left. I got 1 calcium on the right. That's balanced. Now I got to start picking something else. Well, I've got 1 nitrogen in this formula, but I've got 2 nitrogens in that formula, right? NO32. So I don't have the right number of nitrogens. So what I've got to come over here, put a coefficient out in front. Now I've got 2 nitrogens. But the problem is now I've got 2 sodiums on the left. So kind of here trial and error, little cause and effect. I need to come over here and put a 2 out in front of the sodium. Now I've got 2 sodiums on the left, and then on the right, I got 2 nitrogens on the left. I got 2 nitrogens on the right. I've got 6 oxygens on the left, 2 threes. I've got 2 threes, 1 calcium on the left, 1 calcium on the right, and I've got 2 chlorines there, and I've got 2 chlorines there. So everything is balanced. All right, so what I'm going to have you do is this one here on the bottom, a little bit more complicated. I want you to balance this chemical equation here. This is, it's a little sloppy here, calcium sulfate plus potassium phosphate makes potassium sulfate, calcium phosphate. Okay? So I want you to write down this reaction, pause it, and see if you can get the correct answer here. Okay, so when you balance this one, you should get the coefficients 3, 2, 3. I didn't put anything out in front of the last chemical, so that can just be understood as a 1. Okay. So again, does it matter what you pick first or second? No. Just pick an element, make sure it's balanced on both sides. Go to the next element, make sure it's balanced on both sides. If you change one coefficient, make sure it doesn't kind of domino effect back into other ones. All right, so last thing here, I'm going to leave these 2 up. What I want you to do is to write these down. It's kind of video homework whenever after you've watched this to get these answers, and in class show me what you've done, and we can kind of talk about it to make sure you've got the right answers. So that's it for writing chemical formulas. Again, a lot of review in section 1 from chapter 7, and then obviously spending a little time counting atoms in reactions for balancing.